This is the third section of the astrophysics topic. We're going to look at stellar distances. We have to look at ways of measuring stellar distances. There's a parallax method, there's a spectroscopic parallax, and we use Cepheid variables. First of all, we'll look at parallax method. As far as astronomical distances, the numbers end up being very big. So we have a very convenient unit called the astronomical unit. This is the average distance between the Earth and the Sun, and we use this quite a lot. So an astronomical unit is roughly 150 million kilometers, or 1.5 times 10 to the 11 meters. This is not a very nice unit. 1 AU is a nice unit. Now we're going to look at angular sizes. You know that an angle is in a unit called a degree. Okay? Now, we know there are 360 degrees in a full circle. Each degree is split into minutes. There are 60 minutes in a degree. Okay, so that's 1 degree split into 60 minutes. And each minute is split into 60 seconds. And since we're going round a circle, these are minutes of arc or seconds of arc. So there are 3,600 seconds of arc in 1 degree. We need to be aware of these very small angles. So there's 60 arc minutes in a degree, and there are 60 arc seconds in an arc minute. Define the parsec. The parsec is a large astronomical distance, which is roughly 3 light years, but it's defined using this idea of angular distances. This is a distance at which one astronomical unit, in other words, the radius of the Earth's orbit, subtends an angle of 1 arcsecond. So in other words, if you were a distance away from the Earth or the Sun of 1 parsec, and you looked at our galaxy, our solar system, you would see that the radius of the Earth's orbit would be exactly 1 arcsecond. And how do we use this? Because we don't travel away from the Earth, we look at other stars from our position. So this is the distance at which one astronomical unit subtends an angle of 1 arcsecond. So we're going to use basically geometry to kind of flip it round. What we see is that the Earth starts at this position, and if it were to go there, if we look at a star, if it shifts position, because we're looking in this direction, these are the background stars looking vertically upwards, and the star is there. If we move into this position, which is a displacement of 1 astronomical unit, the star is now in the vertical position. The angle is shifted by this angle here, which is 1 second of arc, or 1 arcsecond. Therefore, this star must be 1 parsec away. So, parsec is short for parallax arcsecond, parsec. So 1 parsec is 3 times 10 to the 16 meters, or roughly 3.26 light years. And it's basically defined by the radius of the Earth's orbit, or 1 astronomical unit having an angle of 1 arcsecond. An exercise. Calculate 1 parsec in meters. This is basic trigonometry. We have a very long triangle. And how do we do this? You can do this. You basically, this is the distance of the distance in meters, which we don't know yet. You know what this is. 1 astronomical unit is 1.5 times 10 to the 11 meters. You know what this angle is. It's going to be 1 second of arc, which is 1 second divided by 3,600. So you work out what this distance is. You can use tangent, or you can use sine, because as far as we're concerned, the 2 legs of the triangle are the same size. You should find that 1 parsec is 3 times 10 to the 60 meters. So I need you to do that example now, because you might be asked in an exam. Stellar parallax method of determining the distance to a star. Now, you know that we were talking about this angle here, 1 second of arc. This star moves position of 1 second of arc. But we cannot go from the Earth to the Sun. We can basically only go right to the other the Sun. So this, if it's going to be 1 parsec away, the distance, the change in this angle is going to be 1 second of arc plus another second of arc. So the angle that we measure is actually going to be twice the parallax angle. So what happens is the Sun, the star that we're observing, because it's quite close, will move relative to the background. So what happens is the angle that the star is at appears to shift. The star will change position. We take the baseline, which is the orbit of the Earth, the diameter of the orbit of the Earth. And then we can calculate the distance to the star. So it's like looking at, if you hold your arm's length and you open your left eye, then your right eye, compared to the back of the room, which is the distant stars, let's say, the position of the star or your thumb will shift according to whether you look at your left eye or your right eye. And it's basically because the observer changes position slightly. So we're going to look at this again. So we look at the background stars in that direction, and here's a star there. And then we look at it again. 6 months later, we see that the star has shifted one angle and then another angle. So this is going to be twice the parallax angle, because remember, it's the 1 astronomical unit, which is subtends 1 second of arc. So if we know how big the Earth's orbit is, which we do, we can measure the shift or the parallax, the change in position, and we get the distance. When you're asked to explain how to use a parallax method for finding the distance, you need to say the following things. You need to talk about referring to the position of the star relative to the background stars. You need to talk about the diameter of the Earth's orbit. You need to know that the star moves position relative to the background stars, and this gives you basically twice the parallax angle. And here we have again. So if we calculate this, the tangent of this angle, because we're the adjacent and the opposite sides, is equal to the base divided by the distance. So for very small angles, tangent of an angle is equal to the angle. So it's basically going to be r divided by d. And in conventional units, which is meters and so on, it means that 1 parsec is the radius of the Earth's orbit, which is 1.5 times 10 to the 11, divided by the distance in radians, and we're basically going to get the angle in radians, and we're going to find out that the 1 parsec, that distance, is going to be 3.94 roughly times 10 to the 16 meters. You should try that and make sure that you get the same answer. So we have this answer, 4 times 10 to the 16 meters. Is equal to 3.986 times 10 to the 16 meters. These are not nice numbers. These are not nice units. These are nasty units. We can use the formula to define a new unit. So we know that the parallax is equal to the baseline, the radius of the Earth's orbit, divided by distance. We rearrange slightly. We can swap p and d around. And we have this formula. The distance in parsecs is equal to 1, which is 1 astronomical unit, and we have the parallax angle in arc seconds. This is how we define parsec. So 1 parsec is where 1 astronomical unit subtends an angle of 1 arc second. This is how we can define the unit. So it makes this formula very, very easy to use. Very nice numbers are going to come from this. This is a distance in parsecs. This is a parallax in arc seconds. And these are nice units. So this is how it's presented, I think, in the data booklet. The distance in parsecs is equal to 1, because it's 1 astronomical unit, divided by the parallax in arc seconds. So we look at an example. A star has a parallax angle of 0.1 seconds of arc. What is its distance from us? Well, we know the formula is d is equal to 1 divided by p. The distance we're going to find in parsecs is 1 divided by the parallax, which is 0.1 seconds of arc. So we find that the distance is equal to 10 parsecs. This is as easy as it is, and this is as easy as it gets. Explain why the method of stellar parallax is limited to the measuring stellar distances less than 100 parsecs. Greater than 100 parsecs, which is roughly 300 light years, the distances are so great that the uncertainties become too great. It's not the fact that it's far away, it's that the uncertainties become much bigger, much more significant than the values that we're actually recording. So when they ask this question, they ask it often, you must say that it's because of the uncertainties becoming too great, not the distances. It is too far is not a good explanation. You have to talk about uncertainties. In astronomy, the problem with making these measurements are the uncertainties. How far into a galaxy can we measure distances using stellar parallax? We're talking about less than 100 parsecs or less than 300 light years. You know that the width, like the thickness of the galaxy where we are, is around 10,000 light years. So it's only very, very close stars that we're able to use this method for measuring the distance.